Okay, so the first one people got one, and in the second number they got 2. Okay, great. So this is 1, 1, 2. Okay. And then you apply a one more time. So you do a squared applied to 1, 1. That's the same as doing a applied to 1, 2. So you just take your answer apart. In the first part, you apply a one more time. And I even made the blanks the same. So the next blank is definitely a 2, and then it goes 2, 3. 2, 3. Aha. So then I said there was a pattern. So maybe the pattern is it goes 1, 2, 3. The next one will be 4, right? That's a cubed, 1, 1. Let's see what you guys got for a cubed. 3 and 5. So maybe some people are guessing. It's not a 4. So the pattern, 1, 2, 2, 3, 3, 5, and I ran out of room. Let's put it right here. 8, 4, 1, 1. Actually, okay. Let me make some nice words. Let's try to do it. Put them all out there. So let's do power and answer. So we started with 1, 1, and then we did. So I guess that's like a to the 0. Then we did a to the 1 times 1, 1. And we got 1, 2. Then we did a squared times 1, 1. We got 2, 3. Then we did a cube times 1, 1. And we got 3, 5. Okay. And now we're going to open up a to the 4 times 1, 1. And see what that was? A to the 4 is 5 and 8. 5 and 8. 5, 8. So, what's the pattern? Who can tell me what's the pattern? If I said, please do a to the 6 or a to the 5 times 1, 1, you should be able to do it in 1 second. If you see the pattern, no matrix multiplying. Just use your brain. It's the Fibonacci sequence. That's right. Isn't this amazing? Look, it's the numbers 1, 1. Then it goes 1, 2. Then it goes 2, 3. 2, 3. 3, 5. 5, 8. What's the next one going to be? 8. The pattern is, to get to the next number, you add up these two numbers. 1, 1 gives you 2. 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8 is 13. So if I was going to do the next one, let's move this over a bit. HF it would be 8, 13, and so on. 8, 13. The next one's going to be 13, 21, etc., etc. So hidden in that matrix, this funny matrix A, 0, 1, 1, 1, the rules for the Fibonacci sequence are hidden in this matrix. And that's actually not very hidden if you know linear algebra well. The bottom row is saying, please sum up two things, right? You do the sum of this number and this number when you apply by A. And 0, 1 says, take the second number and advance it to the first one. So if you make this fn plus 1 fn, it says fn plus 2 is fn plus 1 plus fn. So when you go up the Fibonacci sequence, you add up the previous two numbers. That's what the second line here is saying. Okay, so this matrix contains the Fibonacci numbers. Already, I think that's pretty cool. So Fibonacci numbers to me is like number theory, like numbers, patterns, and somehow we put it in linear algebra land. So what is the point of doing this? Why would we put it in linear algebra land? The reason is linear algebra is like the jet engine of mathematics. Linear algebra, we have so many beautiful theorems in linear algebra that can take us anywhere we want to go. So we can use the theorems from linear algebra to try to say something about the Fibonacci numbers. So in particular, I want you guys to notice something, that if we could calculate a to the power n times 1, 1, that's the nth Fibonacci number, or maybe the n plus first, depending on how you do it, n plus first Fibonacci number. So if we can use linear algebra to calculate a to the power n, then we can learn what is fn. We can learn something about fn using what we know about linear algebra. And all we have to do is do this matrix power, a to the n. And so now the question is, how do you do the matrix multiplication? Well, one way is like you guys just did it in the exercise, which is you just keep multiplying, right? So you start off with this one, then you multiply get the next one, then you multiply get the next one, you multiply get the next one, you multiply get the next one, you multiply get the next one. Then you take a break because you're sick of multiplying, then you multiply and get the next one. But like you have to keep doing multiplications, which actually like is how you would get the regular Fibonacci numbers, right? You just add them up. But now the question is, can we do better? Can we do something better? And I want you to think if you can do something better, and then in Mathematize, you tell me, can we do better? Can we do better? That's the question. Is there a way to calculate the value of a to the n without actually doing a lot of matrix multiplication? And your options are yes or no. This is like a test of what did you learn in linear algebra class? Okay, maybe I'll go till it says 2 minutes, then we'll stop. So yeah, try to think back to your linear algebra class.
Do you mean for this A? Or
I mean in general.
in general?
Yeah, in general. If you want, you can say just about this A. Okay, it's true. Okay, this A has a certain nice-ish property that almost most matrices have. There's a certain kind of crappy matrix that's like a little annoying that makes what I'm thinking about more difficult, but you can still do it. So yeah, sure. Let's say it's about this A. This is a good, good question. All right. Let's see what you guys said. Yes, everyone agrees there's a sneaky way. Okay. Put your hand up if you can know what the sneaky way is. Who can tell me what the sneaky way is? Nobody knows what the sneaky way is. Okay, so we're all going to brainstorm sneaky ways. So talk to your neighbors. Think about what could possibly be the sneaky thing in linear algebra that they beat me over the head with in linear algebra class over and over again. There's a super powerful trick to do this. So talk to your neighbors. Try to remember linear algebra class. There's something that they made you do that you should do here. So talk, discuss, and I'm gonna make a text box where you type in what is the sneaky thing. That's what I'll do. Okay, so there's a box. If you have an idea, put in what you think is a sneaky way. If you have no idea, I guess put in no idea. Okay, I'll stop at 2 minutes, but put in either some idea or put in no idea if you have no idea, so I know how many people are in which camp. Okay, I'm gonna stop the timer at 2 minutes. Last chance to put in no idea or whatever you think the sneaky idea is. Let's see. All right, no idea. Good. Mutate the matrix. Okay, I like this. This is a cool word. Eigen decomposition. This is another cool word. So I think mutate the matrix means the same kind of idea as this eigen decomposition. And what it is thinking about the exact same matrix in a new basis. This is one of the big ideas in linear algebra. So this matrix A, you can think about it in the regular basis, and then that's the matrix 0, 1, 1, 1, and we know this gives the Fibonacci numbers. But if you think about it in a different basis, the matrix will transform or mutate. I've never seen this word mutate before, but this is great. The matrix will mutate. We will mutate the matrix into a new form. And if we put it in a form that is very nice to work with, then we can calculate a to the n very easily. So this is like a huge idea in linear algebra, that you can take the same object and look at it differently. So you take it, you stand on your head, and you look at it slightly differently, and it comes out in a different way, and you can all of a sudden you can calculate things easily. And the typical way to do this is the eigenvaluate. So we're going to mutate it to the eigenbasis. The eigen. And when we mutate it to the eigenbasis, we're going to get a really nice thing. So who has seen this kind of thing before, but it's a little rusty from linear algebra class? Who's never seen this kind of thing before? Okay, so again, I'm glad we're doing this example because PCA, what we're about to do, is the exact same idea. We're going to have a certain matrix, we're going to look at it in a different basis, and we're going to hope that that basis is nicer to work in. So let's do it for this matrix, 0, 1, 1, 1. And okay, I won't do all the details, like I won't do a full linear algebra class calculation of the eigenvectors and eigenvalues. I'm going to show you some hints of what's going on, and I'm going to give you the final answer, and I'll point you to a note where you can see the full thing if you want. But here is the first thing. I'm going to make phi. Phi is going to be the golden ratio. 1 plus the square root of 5 divided by 2. This is the golden ratio. And you might know that the golden ratio is related to the Fibonacci numbers. Okay, I can't help but resist that. I got to tell this story. So when I was in high school, I was in charge of the math club, and me and a friend of mine, we did a whole lecture about the golden ratio. Say phi this, phi that. Oh, look at those phi's over here. It's in your credit card. It's in the ancient Greek sculptures. Phi this. Everyone's like, Everyone nodding. At the end of the lecture, someone says, okay, but why did you write 5 with a funny squiggle like that? Isn't it 5 like? Okay. So this is why it's important to get some audience feedback. So this is phi, not 5. Okay. Phi is the golden ratio. What the hell does this have to do with anything? Let me show you. Here is a little magic trick. 0, 1, 1, 1. I'm going to multiply it by the vector 1, phi. The vector 1, phi. Okay, what do you get when you do 1 phi? Well, you know, so you get 0 times 1, 1 times phi is a phi. And here you get 1 plus phi. 1 plus phi. Okay, that's kind of boring. But here is the real magic. Phi times 1 plus phi is actually phi times 1 phi. And that is because phi squared equals 1 plus phi. This is the magical thing that makes the golden ratio golden, is this equation. Another way to say this is phi is the ratio, phi over 1 is the ratio of 1 plus phi to phi. That's the same equation. And this is something about proportion. So if you have a rectangle and its side lengths are phi and 1, and then you make a 1 by 1 square out of it by cutting a 1 by 1 square, the little thing you get over here is the same aspect ratio. It's the same phi to 1 ratio, but sideways. And I guess credit cards are supposed to be like phi by 1. Let's see. So they're like that. So if you cut a square out of your credit card, the little thing on the side is supposed to be phi by 1. I don't actually know if credit cards these days are, but so this is why phi is beautiful or whatever. I don't know if I buy in any of that architecture aesthetic stuff, but this is certainly true. Okay. So what just happened? We fed in the vector 1 phi, and we got the same vector back, but multiplied by phi. And what this is saying is that phi is an eigenvalue of this matrix. This is the eigenvalue equation. And not only is it an eigenvalue, the vector 1 phi is an eigenvector. Okay. The same thing actually holds for the other root of this equation. So phi satisfies this. There is another root of this equation. So phi is 1 plus the square root of 5 divided by 2. If I make beta be 1 minus the square root of 5 divided by 2, I'll have the same thing. 0, 1, 1, 1. And 1 beta will also be beta times 1 beta. And this is the other eigenvector eigenvalue for the matrix. And what we're going to do now is we're going to think about the matrix. How does it act on linear combinations of the eigenvectors? So instead of looking in the ordinary land where you have vectors which are a comma b, we're going to look at vectors that are linear combinations of 1 phi and 1 beta. So this is the basis we want to work in. We want to work in the basis 1 phi and 1 beta. And when you work in that basis, what is the matrix doing? Well, it's returning copies of 1 phi and 1 beta. And when you hit it with 1 phi, you only get a 1 phi. There's no 1 betas. And when you hit it with a 1 beta, you only get a 1 beta. And what this is saying is that the matrix 0, 1, 1, 1 is diagonal as long as you work in this basis. So this special basis, the eigenbasis, in the eigenbasis, the matrix is a diagonal matrix, and you can see exactly what it's doing. So to make it maybe even more crystal clear, let me write it another way. Here's the other way. 0, 1, 1, 1 times some linear combination, a times 1 phi plus b times 1 beta. So we're doing linear combinations of 1 phi and 1 beta. That is going to be a phi times 1 phi plus b beta times 1 beta. So it's very easy to calculate what the matrix 0, 1, 1, 1 does as long as you describe the input this way. This is a nice way of saying the matrix, if you wrote it in this basis, would be the diagonal matrix phi beta. So let me show you what that means. So the matrix 0, 1, 1, 1 in some sense is equal to, we start by saying equals in quotes. It's equal to the diagonal matrix phi 0, 0, beta. What do I mean by it's equal to? I mean equal if you work in the basis 1 phi, 1 beta. Right? So the matrix phi 0, 0, beta, if you hit it with some vector AB, you would get a phi b beta. This equation is exactly what we have here. When you hit it with AB, you get a times phi and b times beta. That's exactly what we had already. So in some sense, this matrix is acting just like that matrix. We just have to change into this basis. And how do you do a change of basis? Well, one way to do it is to just make a matrix out of the eigenvectors. So I'm going to get rid of the equals in quotes and this idea of working in the basis. I'm going to make an actual equal sign. And the actual equal sign goes like this. You take the vector 1 phi, 1 beta. You put that here. And what this is saying, take the output of this and make it a linear combination of 1 phi and 1 beta, just like we have here. And then I got to do the opposite conversion over here. So here I got to put in 1 phi, 1 beta inverse. And now, this is an honest to goodness actual equation that is true. The matrix 0, 1, 1, 1 as a matrix is equal to this matrix of eigenvectors times this matrix of eigenvalues. So this is a diagonal eigenvalue matrix. And this is the inverse of that matrix. So what this is saying is if you want to know what 0, 1, 1 does to some vector, first you take the vector and you convert it into the basis 1 phi 1 beta. You write any vector as a linear combination of 1 phi 1 beta. Then you do a diagonal operation and then you convert back. So this is called diagonalizing a matrix. This is what mutating the matrix into the eigenbasis is. And what this is showing us is that the matrix 0, 1, 1, basically anything you want to calculate about it, you can instead calculate on this matrix, phi 0, 0 beta. Okay, so this is like review from linear algebra. If you've never seen this before, I'm going way too fast. If you did a really good linear algebra class, this is all boring. But this is a good time to stop. Maybe there's some questions that would help clarify. Or not. Does this look familiar? Something inverse, diagonal in the middle. Okay. How is this helpful? Okay, what the hell is the point of it? I think this is the thing that gets lost in linear algebra class. So in at least my linear algebra class, they tortured us and they just said, diagonalize the matrix. And they just like hit us with a stick until we diagonalized the matrix. Like, okay, look, we did it. Leave me alone. What's the point? Why would you do this? Why are we doing this? Who cares? I'll tell you why. Because now we can solve our problem. 0, 1, 1, 1 to the power n. That's what we wanted to calculate, right? The nth power of this matrix. And this is some crazy nasty thing. Like you have to do a whole bunch of additions, figure stuff out. I don't know how to do the nth power of this matrix without doing n matrix multiplies. I do know how to do this one. This one I can do, phi 0, 0 beta to the power n. That's easy, I can do that one. Because it's diagonal. It's so nice. Like this one is phi to the n is 0, 0 beta to the n. So I can do the nth power of that matrix. This one I don't know how to do. But I just said that this matrix is the same as that matrix as long as you work in the other basis. So if you want to know the nth power of this matrix, it's the same exact thing. This is literally true. The nth power of this matrix is the same, if working in this basis, as the nth power of this thing. And look, now we have something for free. I can calculate the nth power of this matrix with no matrix multiplies. Okay, that's a lie. I have to do 2 matrix multiplies. I have to do exactly 2, no matter what n is. And all I have to do is work at this beautiful basis where things become Greek letters, and it's a diagonal matrix. Another way you can see this that is rather cute, right? This was the matrix A. Let's call this matrix V for eigenvectors, and we'll call this matrix D for diagonal. So we had A is V, D, V inverse. That's what we said. If A is V, D, V inverse, then what is A squared? Well, it's V, D, V inverse times V, D, V inverse. And look at what happens. The V inverse and the V are next to each other in the middle. So if you kill the V and the V inverse, they cancel out. I should say they simplify to the identity. V inverse times V is the identity. And so you're left with V D squared V inverse. So there's a nice way with algebra. You can see this thing directly if you don't believe my eigenvalue stuff. But now we're in business. 0, 1, 1, 1 to the power n. It's actually just this matrix phi 0, 0 beta to the power n. And that, because it's a diagonal matrix, I can bring that in and calculate it explicitly. Yeah?
Sorry, can you go over again how you got the eigenvectors?
How did I get them?
Yeah.
So I did a little cheat on that because I didn't start with the matrix and say, what are the eigenvectors? I said, here's the matrix, let me pull out of my pocket this vector, boom, it's an eigenvector. So I skipped the step where I actually found the eigenvector, and I just showed you a vector, and I convinced you that it was an eigenvector. If you want to actually find it, what you have to do is the characteristic polynomial, or something like that. So you look at the determinant of A minus lambda I, which is the matrix minus lambda 1, 1, 1 minus lambda, and you do the determinant of this matrix, you find where the zeros are and so on, and then you solve a linear system. So this is all stuff from, this was the boring part of linear algebra class. I'm trying to show you the fun part. Yeah, so that's a good point. So I skipped the step where I actually found it, and I pulled it out of thin air, and I said it better way. It turns out if you do this, you're just going to get that the polynomial we had before. Lambda squared equals 1 plus lambda. So it's not surprising that phi and beta appear. Those are the two roots of the polynomial. Yeah, that's a good point. And I do have a longer note here with the full details. So if you really want to remember how exactly it works, you can read it. Great question.
And what would be the value of beta?
So beta is the same thing with a minus. Let me write what beta. Beta is 1 minus the square root of 5 divided by 2. So phi and beta, they both come from the same quadratic equation, one of them with a plus and one of them with a minus. So they're both the roots of this equation. The determinant of that matrix equals 0. Okay. Okay, so what's the point of this? I know, now I have a formula for 0, 1, 1 to the power n. So now I can give you a formula for the Fibonacci numbers, guys. This blew my mind. I was like, you can't make a formula for the Fibonacci numbers. You have to sit there and grind out the pattern, right? No, you don't. So 0, 1, 1 to the power n times 1, 1. This is the nth Fibonacci number. This is fn plus 1 fn. That's what we said in the pattern this morning. And now I have a formula for this thing, 0, 1, 1, n. So there's two density matrices, but the thing in the middle is phi n and beta n. And if you just calculate what these are, it's not so hard. So it's like, doing the inverse of a 2 by 2 matrix. That's what you have to do. So I'm going to skip a couple steps. But basically, so I'm going to put a dot, dot, dot. I'm skipping a few steps. So the Fibonacci number fn, you can read it from this matrix to the power n applied to 1, 1. You have a formula for this. If you calculate what it is applied to 1, 1, you get a formula which says this. Fn is, and let me make sure I get it correct. It's phi to the n minus beta to the n. Phi to the n minus beta to the n. And then you have to do one thing. You just have to divide by the square root of 5. Okay. Where did the square root of 5 come from? It turns out there's a square root of 5 in this inverse matrix. So if you calculate this inverse matrix, there's a square root of 5. That maybe is the only mysterious part. I'm telling you, it's hidden in here. If you actually calculate what this is, it'll have a square root of 5 in it. But the phi to the n and the beta to the n are exactly from our diagonal matrix. So this is a formula for the Fibonacci numbers. This is a formula. I can do, people always do this to test their programming skills. How quickly can you program the Fibonacci numbers? So I can calculate the billionth Fibonacci number. You take phi to the power 1 billion, subtract beta to the power 1 billion. It turns out beta is quite close to 1. So if you do beta to the power 1 billion, you just get 0. I want to show you guys. This is too cool. We can't resist. Okay. So let's go to Wolfram alpha. Here we go. Phi is 1 plus the square root of 5 divided by 2. That number. And then we have 1 minus the square root of 5 divided by 2. And I want to take them to some powers. What number do you guys want to know? Someone yell out which Fibonacci number you want.
Maybe 10?
10. Okay, 10 is a good one. Let's do 10. So we'll take this to the power 10. We'll take this to the power 10. Oh, and I said I'm supposed to subtract them. Okay, so that's phi to the power 10 minus beta to the power 10. And we got this crazy number, 122.983. Uh-oh, what went wrong? You have to divide by square root of 5. So phi to the n is crazy irrational number, beta to the n, crazy irrational number. You subtract them, divide by 5, boom, you get 55. So if I divide the whole thing by the square root of 5, then you get 55, which is the 10th Fibonacci number. That's my magic trick. Thank you very much. Okay, this is the craziest thing. This blew my mind when I first saw it.
Just curious.
Yeah.
Why don't you do like 1,000?
Let's do 1,000. Yeah, 1,000.
I wonder when will it get overflow?
I don't think you will ever get an overflow. I think it'll be okay. Okay. I mean, it calculated it. It's just that the 10th Fibonacci number is like 10 to the 200. So here's the thing. The second number, 1 minus square root of 5 divided by 2, is less than 1. So the second number basically doesn't matter. You take like 0.5 to the power 100, it's like 0. So basically, this is telling you this is approximately phi to the n over square root of 5. So you kind of don't need the second number, which actually also explains Okay, this explains why you can use the Fibonacci numbers to convert from miles to kilometers, but I won't do that. I think we've spent enough time. I'll do that another day. So yeah, there. This is to me, this is the quintessential power of linear algebra, right? You take a problem that's got nothing to do with linear algebra, you look at it as soon as you can write it as something involving a matrix. If you can diagonalize the matrix and think in terms of the eigenbasis of the matrix, all of a sudden you like own the problem. You just like, you know everything. It's all there. This is exactly what we're going to do for PCA. So we're going to start with a data matrix, which is going to be quite messy. And the secret is, if you want to know what's going on in the data matrix, just diagonalize something. Okay, we're going to have to find out what the something is. And all of a sudden things will simplify, and you will be able to have a sort of simplified version of your data. And in today's class, we're going to do it with regression. So we're going to see how it interfaces with regression. On Tuesday's class next week, we're going to do sort of unsupervised learning, where you just have the x's, and we see what you get out of this diagonalization type thing. So that's what we're going to do at a very high level. I gave you this little linear algebra recap lesson so that we're going to be in the middle of some complicated calculation, and I'm going to say, now we do the eigenvalues, so you got to keep that in your brain. Any questions or comments? Okay, so you guys are ready for the PCA. So this all was linear algebra recap. Now we're going to do PCA. And PCA is this idea, principal component analysis, which is that when you have a data set and it looks something like this. So here's my data. I drew it in Desmos. And this data set has like 15 points in green, excuse me. And the thing about this data is it looks a lot like the x1 and the x2 are correlated. So think of this as x1 and x2. So there are a lot of ways you could deal with this x1 and x2 being correlated thing. So one thing you could do is you could just delete one of them. You could say, here's my data, x1 and x2 are very highly correlated, so maybe I don't need x2. I just use x1, right? That is something we talked about in the course, and we decided that's not a great idea. You're just sort of like deleting data out of nowhere. But another idea is, could we sort of combine x1 and x2 together in such a way that the redundant information is sort of like minimized or like left over? That's what this PCA idea is. Can we do linear combinations of the original data to get a situation where we sort of separate out what is dependent and what is not? So right now the x1 and the x2 are all mixed together and they're very correlated. Could we do a linear combination of x1 and 2 over here and a different linear combination of x1 and x2 over here, so that we know this part is like how they're going together, and this is like the leftover stuff. That's this PCA idea. And to make it even more precise, I'm going to take this data, I'm going to do a linear combination. What is a linear combination? You can always think about it as projection. So I have a blue line, and I'm going to take my original green points, and I'm going to project them onto the blue line. And this has a nice little slider. So by the way, you can play with this if you want on your own. So I can choose any direction I want for the line, and then I can see what it is. So this little data point, I can slide around so you can see what I'm doing. I'm just taking the data point and I'm projecting at a 90-degree angle down to this blue line. And when I do that, I get a sort of a transformed data. So depending on which direction I pick, I can play with the data and make the data look different, right? And the idea is, can we take this two-dimensional data and project it down to this one-dimensional line in such a way that we sort of preserve the information that we want? This is the idea of PCA. We're doing linear combinations of the green, which is the same as projections onto these blue, and can the blue dots give us the information that we want without having to think about the green dots? And the blue dots are nice because they're one-dimensional. They only live on one line. So we'll have effectively reduced the dimension, right? From the green dots are two-dimensional, we reduce it down to just a one-dimensional blue thing. So it's a nice idea. There is one problem, and that is which direction should we pick, right? You see there's more than one choice. In fact, there's infinitely many choices. You can make this blue line go any way. So we need a way to decide which way is the best line. That's what we have to do. And so again, we're trying to think of taking the green data and pushing it down onto the blue line, which direction would be the best? And I have two options for you guys. Which direction would be the best? To pick the best direction, I have two options. Make the projection of the points as spread out as possible, or do we want to make the projection of the points as close together as possible? So I'm just thinking about where these blue dots end up, and do we want them to end up all together, or do we want them to end up all far apart? And then, once we decide exactly what we want to do, we can do our usual thing. We make a loss function, we maximize it, that kind of stuff. So take a stab at this. Tell me what is the best thing we should do.
Here are flipped formulas that we're seeing on the screen.
By default, there's a button that randomizes it for each student. And if I don't uncheck the randomize button, it'll randomize it. So yeah, I probably forgot to check the button. That's why. Okay, well, that's 8 people. Yeah, I'll stop at 1:30. So you have 20 seconds to put in your answer if you're the last person. Okay, I think there's 10 people in the room. Okay. Let's see what people said. Make the projection of the points as spread out as possible. That is correct. So that's the correct answer. Why do we want to do that? So let's see kind of like intuitively why we want to spread them out. So, if you put them like this and you project the data like that, you've made all the points close together. And now the problem is you can't tell the points apart very well. So like this point and this point seem very different. But when you project them onto a line like this, and they're all together, they're all kind of indistinguishable, or they're less distinguishable from each other. Whereas on the other hand, if you do something like this, then the points are as spread out as possible, and you can tell them apart very well. And so kind of what we want to do is we want to reduce the redundant information, the stuff that doesn't tell you how the points are different. And you want to keep what makes them different. And so that kind of leads to this idea of spreading them out. Okay, so this is good. Like, we're going to spread them out. How do we measure how spread out they are? This is the thing that we have to decide. So, we need a number that tells me how spread out they are, and then we can maximize that number. Does anyone have an idea of how you would measure how spread out things are?
The variance.
The variance, yes, this is the first thing we did in the course. So you can do the variance of these points. The variance is the same as the sum of the squares of the distances. So I have this little folder over here called score. And I'm doing the root mean sum of squares. So it says sum of squares, but I think it's actually the square root, the root sum of squares. So I just sum over all the points, and I take the difference squared, and I add it up, then I take the square root. So the root mean squared, the RMSE error. And you can see it depends on which direction I pick. So if you pick a direction like this, you have a very small root mean squared error, tiny root mean squared error. And as you swing around here, it goes up, 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 up. It keeps getting bigger and bigger and bigger until you kind of reach a plateau, and then it's going to start to fall again, right? And the thing is, we want to spread them out as much as possible. That means make this as big as possible. So where is that? 4.651, 65. Can I beat 651? Okay, so it's right there. That's the best direction. And okay, just to make sure this is crystal clear, I'm literally, this orange thing is how much these blue points are spread out along the blue line. So an easy way to see how much the blue points are spread out along the blue line is to, once you put them on the blue line, and you see what they are, you draw a copy of them on the red, on the x-axis. So let me show you what that looks like. So here is the exact same thing. I'm doing the same information twice, once in blue and once in red, just so you can see them on the x-axis, so you can see how we're calculating the sum of squares. And the other nice thing about doing it this way is calculating the formula for the blue points is kind of annoying. So again, it's like a linear algebra class exercise. It's about a projection of something onto something else. But calculating the red points on the x-axis is very easy, and it's labeled with exactly what it is. It's just dot products. So the red points let me write this on the board. This will be useful for us. They are just dot products. So the projection of the point x onto the line, let's call the line L. This is somewhat complicated. It's not super complicated, but it's annoying. It's a linear algebra exercise. So that's in blue, the projection. But if you just want to know how far along is the projection, so let's say how far is the projection of x onto L. It's very simple. It's the dot product of x and L. That's all it is. So you take the dot product of this line L, and you just take the dot product with the green thing, and whatever you get, you get. So a good example is let's pick one point, and let's make the line, so if the original data point goes through the point, then you just get the length of the point. If you're perpendicular, it should go to 0. So that red dot, if I make this perpendicular, goes to 0. So it's all quite simple. I guess this is assuming that the norm of L equals 1. So if you don't assume that the norm of L is 1, then you're going to inflate or deflate by the size of L. Another way you could write this is x times the cosine of the angle. Theta is the angle between x and L. Okay, so this is projections. Yeah.
X, do you mean the green dots?
X are the green dots. Yeah, that's right. So this is saying that if you want to get where the blue dots are, you have to do something a little bit complicated. But if you want to know where the red dots are, it's literally just this, right? The red dots just have one coordinate, and the value of the coordinate is how long the original point was times the cosine of the angle with the blue line.
So you mean green dots, the blue gives you the red.
That's right. Yeah. So x, this is the green, and this is angle between dot and blue line. Okay. So very simple, and it's nice. Linear algebra is appearing everywhere. Okay, and now we're going to do a little bit of math, and we're going to set up this problem of maximizing the sum of the squares. So we can use this formula, and we can try to write down what it is, the sum of the squares. And we're going to see that maximizing the sum of the squares is going to lead to something about a particular matrix. So that's what we're going to do next. Okay. And again, we're going to use this formula. So this was for one dot. I just have to redo this for a bunch of dots. So I'm going to have X, which is the data matrix. This is the same thing we had the other day, data matrix. So this is I'm going to call it an n by, I'm going to use p for the number of parameters. N is the number of points, and p is the dimension of each point. So in this example, on Desmos, the number of points is like 10. How many points do we actually have? At 11. So we have 11 points, and each point is two-dimensional. Each point is two-dimensional. So it's we had this matrix before. It's got a lot of rows, 11 rows, and 2 columns. It's a big skinny matrix like this, right? X1 all the way to X2. Right. X11, right. Okay. And I'm going to transform it by finding a direction L. And what you get is the transformed points. The transformed points. T are going to be the transformed points. So those are what I'm calling these red things. And T is just going to be X, which is 11 by 2, or n by p more generally. And I'm going to hit it with one vector L, which is going to be a p by 2. Is that what I'm going to do? Give me one sec. I see. Okay, just that. Yeah, p by 1. Okay, I just want one vector. Yeah, okay. It's p by 1. So if you do this, you have transformed t is the transformed data is going to be one-dimensional. This is going to be n by 1. And this makes sense, right? We're taking our two-dimensional data points in green, and we're transforming down to this one single direction, the red points. So this is going to be a vector. I'm going to call it T vector so we don't get confused. So is that clear what we're doing? We're taking our data points, we're projecting them, and projecting them just means doing a matrix multiplication. That's exactly what an inner product is. An inner product is a matrix multiplication of a one row thing. This is a thing with n rows. We're doing n inner products. Yeah.
I'm wondering if 1 should be replaced by m or not.
So okay, this is a great question. So right now, I am trying to find out just one direction.
Okay.
So it's true, I'm taking my two-dimensional data and I'm trying to figure out what is the best way. I'm transforming it down to one dimension. So I'm going from 2 dimensions down to 1 dimension. And in general, no matter how many dimensions you have, you can think about transforming down to 1 dimension. Of course, maybe 1 dimension is not good. Maybe that's too squishy, right? We have 100 dimensions, we squish down to 1. That maybe is a bad idea. But we're going to see that to get it squished down to 2 dimensions, first you sort of squish down to 1 dimension and you see what's left over. So we're going to see in a second, this 1 will get replaced by something else. But for now, it's just going to be 1 dimension. So this is a good point. And again, it's because I'm thinking of this limited problem of 2 dimensions down to 1 dimension. Yeah, great question. Anybody else? Okay, so those are the points. And I want to do the root mean squared, so the variance, the mean squared error. So the mean squared error of points t. Okay, it's not really an error, right? I guess it's just the mean squared. So the mean squared error, we had some targets, and we were trying to say how far away were we from the targets. In this one, we're just trying to make sure they're spread out as possible. So I guess the target is 0. We want everybody to be as far away as possible from 0. So I won't say mean squared error, I'll just say mean squared of the points. And we want to maximize. We want to maximize. Okay. So this is like a little bit the opposite of what we were doing earlier in the course, where we try to minimize the error. Now we're trying to maximize how spread out the points are. So what does that mean? That is exactly the norm of t squared, which is the sum, if you want, 1 over n sum from I equals 1 to n of ti squared. Okay. And you could write this, you could take this formula and write it out and see what it is. But if you write it as a vector and think of it as the norm of a vector, so this is an n by 1 vector, and you use this formula, you're going to get something nice. So this is 1 over n, x times L, x is a matrix, L is a vector, squared, right, because t is xl. And xl, the norm of something squared, you can write as the vector times the vector transpose. So the norm of v squared, you can write as v transpose times v. So we can do the transpose of this times itself. So we do xl transpose times xl. I keep writing the vector signs on the x's, even though x is a matrix, L is the vector. Okay, and there's a 1 over n. All right, let me do one last step. The transpose of x times L is L transpose times x transpose. So we're trying to make sure the points are as spread out as possible, and if you write down what that means, what it means is you're computing for every direction L, you do L transpose x times L. And now you should go, aha, wait a second, we saw this before. X transpose x. This was on the board last week, or maybe earlier this week. Does anyone remember x transpose x? Let's remember, what is x transpose x? So x is an n by p matrix. X transpose is a p by n matrix. And when you multiply them together, you get a p by p matrix. So in this case, it's a 2 by 2 matrix. It's a 2 by 2 matrix, and it has something to do with summing over all of the n examples. And to jog your memory, in case you don't remember, I have a notebook. Is it this one? Okay, so here's this is kind of the exact same stuff as in Desmos. but now in Python where we can make some more fancy plots. So here are the original points. They look very similar to the ones in Desmos. And here I have a function that makes the x transpose x surface. So it's going to plot this thing, this quantity, as a function of L, right? And in it, I called it W. I called it W, not L. But what we're doing is we're plotting the norm of x W squared. Norm of x W squared. Here I said it's the norm of x L squared. We're plotting this thing as L changes. So you give me L, I calculate this value, and then I plot it. So it's going to be a surface plot. And here is what it looks like. Does that look familiar? So this is W1, or if you want, it's L1. This is W2. And I have plotted on these contours the value of this thing, right? This quantity, x, the norm of xl squared. Okay, and if L equals 0, it's 0, so it has a minimum at 0. And if, as L gets bigger, you get bigger values. But not all directions are the same. This is the interesting thing. So if you go this way, the directions get bigger, or if you go in this direction, the values get bigger faster. So you have to imagine this as like a big bowl coming out of the screen. The values get bigger faster. And if you go in this direction, or in that direction, it's like a big valley, right? It's very long. This is exactly the same thing as the surface of the mean squared error that we had last class. And that was the exact same matrix, x transpose x, right? The only difference was this one is centered at 0, and that one was centered somewhere else. That one had a center somewhere over here. And that's because the mean squared error is not minimum when you estimate 0. The mean squared error is minimum when you sort of pick the best possible parameters. But this matrix, x transpose x, is the same matrix as before. This is a linear shift, just a translation of what we were doing before. And I've plotted these two red directions. Those are the two eigenvectors of the matrix x transpose x. And basically, what's going to happen is to solve this problem, which direction is the best way to go, it's going to come down to, well, it's always an ellipse with the directions being the eigenvectors, and how fat you are in each direction are the eigenvalues. So if you know eigenvectors and eigenvalues, you can find the best possible L, no problem. And that's what we're going to do now. Any questions or comments about this? I will say it's exactly this, it's the tricky thing. It's the same problem as the mean squared error. Before we had x beta, now we have xl, or xw. But it's the same linear algebra as before. Okay. So we're gonna let's think about this maximization problem. Find the maximum, and I claim that the maximum happens in one of these two special directions, right? So if you want to go like in between these two red arrows, like you go straight up, that's not the maximum, right? And you really should think about it as living in a bowl and trying to find out which way would be the fastest way to go uphill, right? And in this case, the fastest way to go uphill is this direction. Is this direction here. You're going up very quickly. If you go that way, that's the slowest possible direction. So let's see what this looks like. So once again, we want to find L to maximize. So this is what we want. We're trying to find the L that maximizes this. And just like before, you might think this is a crazy problem. How are we possibly going to do this? X transpose X is some insane matrix. But if you look in the eigenvector eigenbasis of X transpose X, this is a very boring matrix. So in the eigenbasis, so this is just like we did for the Fibonacci numbers. It looks like a complicated thing with a complicated matrix. X transpose X could be anything. But if you look in the eigenbasis, this becomes very simple. So this becomes 1 over n L transpose. Let me put the 1 over n in the matrix. 1 over n is in the matrix. So we're going to do the eigenvectors of 1 over n X transpose X. But if you look in the eigenbasis, this becomes a diagonal matrix. So you're going to have a lambda 1, lambda 2 all the way on the diagonal, all the way up to lambda p. It's a p by p matrix, X transpose. And I'm saying this is equal to lambda 1 all the way to lambda p. So we're looking at the crazy matrix, we look at it in the eigenbasis. Okay, and when you do this, now L1 will never interact with L2. L1 will stay on its own because it's a diagonal matrix. So you end up with, I don't know if it's worth writing it, but it's going to be the sum. Lambda 1 times let's write it out without a sum. Lambda 1 times L1 squared plus lambda 2 times L2 squared all the way to lambda n times Ln squared. So the nice thing about this is that if you write it in the eigenbasis, it's very easy to write down just in terms of the L's. L1 does not interact with L2. There are no terms in this that are like L1 times L2. All the terms are just L1 squared, L2 squared, and so on. Okay, so how do we maximize this? Which L maximizes this? Okay, and maybe I'll make it a little bit more tractable by saying, let's suppose lambda 1 is the biggest eigenvalue. So we'll say lambda 1 biggest, lambda n smallest. So let's pretend the eigenvalues are in order. So you have this linear combination, lambda 1 times L1 squared, all the way up to lambda n times Ln squared, and you want to make it as big as possible. What vector should you pick?
Choose L1 bigger.
Yeah, this coefficient is the biggest. Why don't we make L1 squared as big as we can, right? How big can we make it? Well, like we said before, you have to make sure the line is norm 1, right? You can't cheat and just make your line vector twice as long. That represents the same line. So this is actually subject to the norm of L equals 1. So you have to pick something whose total norm is 1. So it's this, and if you want, you can say subject to L1 squared plus L2 squared all the way plus Ln squared has to be 1. The sum of the squares of the L's has to be 1, and you want to make this thing as big as possible. So what do? You just put all of your eggs in the L1 basket. You make L2, L3, all the way up to Ln 0, and then you make L1 equal 1, and then you just get lambda 1. That's the biggest you could possibly do. And it's actually quite easy to prove, right? If you have any other weight in any of the other ones, that's less than you could have gotten for L1, because we said lambda 1 is the biggest. So the solution is very clear. You make L1 equal 1, and you make all the other ones 0. But we're working in the eigenbasis, so saying L1 equals 1, that says put everything in the direction of the first eigenvector. And you can see that visually on our screen, right? On our screen, the best way to go, the best direction is this eigenvector. This eigenvector is the best. That's the eigenvector with the largest eigenvalue. Did I write the eigenvalues down as well? I did something with them. Oh, I transformed the points. Okay. So this is what PCA is. This is how we find the best possible direction. It turns out just to be the eigenvector of the matrix X transpose X. So this is called the empirical correlation matrix, because it's sort of the correlation of all things. You find the largest eigenvector, and that direction is the best way to go. So this is the best way to go. So now you can transform all these blue dots into red dots, and that is what I have plotted on the y-axis here. On the y-axis here. So I transformed the projection. I used the direction, which was the eigenvectors. So I calculated the eigenvectors of the matrix X transpose X here, and then I just did this projection, which is a matrix multiply. X multiplied by the eigenvectors, and then you get the transformed points like this. And on the y-axis, I've transformed them according to the largest eigenvector, and on the x-axis, I made it according to the other eigenvector, right? So if you did a one-dimensional thing, it would just be just the y values here. And to keep the data two-dimensional, you can use the other eigenvector. So let me talk about this idea. So far we found the maximum, and let me talk about everything else. Okay, so best possible one-dimensional 1D slice if you want, or let's call it 1D projection. Is the largest eigenvector. So that's the best possible 1D. What would you think is the best possible 2D one? And maybe we'll go into more detail about this next time. But I think if you understand the 1D thing, that's like 90% of the battle. The best possible thing is the largest eigenvector. What would be the best possible 2D projection? So in this particular problem on Desmos, the whole problem is two-dimensional. So once you've projected onto some direction, the only thing you can do is project onto the perpendicular direction, because there's only 2 dimensions total. But if the green original points were in 10 dimensions, we figured out one direction to project them onto. What would be left over? Well, it turns out, so I'm not going super into it. The best possible 1D projection is the largest eigenvalue. That's because you have lambda 1, you want the sum of the squares to be 1. We talked about that. What if you had 2 directions to put it in, right? Well, you could take this best direction, and then what would be left over is lambda 2. So it would be the second best possible, the second eigenvalue. So the best possible 2D projection is the top two eigenvectors. Okay. So, and in general, you can make projections, a 1D projection, or a 2D projection, or a 3D projection, any number you want, by projecting onto the eigenvectors in order of how big their eigenvalue is. And the biggest eigenvalues are sort of the most important, and the smallest ones are the least important. And we're going to spend a lot of time on Tuesday's class talking about exactly this. So we'll see some real life examples and so on. Okay, but this is the math behind the transformation. And here is the very simple example, kind of going along with the Desmos thing. So we started out with these. What did we do? We started out with these data points, and then we created this surface of doing projections in different ways. And the surface ends up just being something involving the matrix X transpose X. And the matrix X transpose X, if you work in the eigenvector basis, it's very obvious what to do. The best projection is this red direction, and the second best is that perpendicular direction. And so if you transform the data like that, now the data looks like this. And in some sense, this data has been spread out as far as possible in the x2 direction, and it's, whatever is left over is in the x1 direction. So we sort of found a way of automatically taking this data and automatically finding this direction that corresponds to how it's changing. Okay, that's a summary of what we did, and we're going to spend more time on Tuesday's class doing related stuff. I have one more quick little thing in Python I can show you, but this is a good time to stop for questions, because I know it can be kind of a lot all at once. Yeah?
Sorry, in case of interpreting the coefficient when we decrease the dimensions.
Yeah.
So it seems to me we should transform the coefficient to the original number of parameters and then interpret it. But
yeah.
Anyway, is there any way that we should interpret the decreased dimensions actually?
Yeah, so I think there is no nice real life interpretation of the things. And so I think what you can say is it's a linear combination of other things. So to give a very simple example, I just said this is data, right? But let's pretend the x-axis or the x1 is height and the x2 is weight, right? And of course height and weight go together, right? If you're taller, you're more likely to weigh more. So what did we transform it into? Well, we did this vector, right? Essentially the 1, 1 vector. And so that means we did a combination height plus weight. So our new axis is something like, after we transform it, on one axis we have height plus weight, and on the other one we have height minus weight. Again, do these have real life interpretations? Well, you can sort of imagine them, but the thing about real life is you can't actually subtract a height from a weight, right? One's in kilograms and one's in meters. and you can't add them. So the only interpretation I think that you can always say is it is a linear combination of the original things, and it is done in the way, in order, so that they're as spread out as possible. That's like what you can say. And so maybe you can go back and say something like, oh, the height plus the weight is your like siziness. That's your new index of siziness, right? So you can make something up like that. And it's a linear combination of the things. But in general, it'll just be some crazy linear combination of everything, and it is what it is. Yeah.
But I'm thinking the final result of doing these analysis is interpretation.
So I think the final result is going to be the thing that is most useful for is reducing the dimension. And so far we've only done a two-dimensional example where you don't really need to reduce the dimension. I can already plot it in 2. But the reason I did this was to make it crystal clear what's going on. So next class we're going to do higher dimensional examples, and then it'll be more useful to reduce the dimension. So we start out with something that is 100 dimensional, and we reduce it down to 2 dimensions that explain most of what's going on. And so that's quite a powerful thing. So I think that's what it's best useful for. So I will give you, I also have a 5-dimensional example. Which we'll go over next class too, but let me give it to you very quickly now. So this is the same example as we did in class a few classes ago, where we had this nasty correlation matrix. And so we had x1 to x5, and they're all very correlated. And the question is, how do we reduce? They're all very correlated, should we just delete the variables? What should we do? And in that class, we looked at 2 possibilities. We said, okay, you have 5 things, you could just delete all but one of them, and because they're correlated, you could cross your fingers and hope that, okay, the stuff I deleted doesn't matter, right? That was one possibility. The other possibility, we said, oh, you do subset selection, you just let the computer try all the possible subsets, and it'll figure out, oh, x1 and x3 together, delete x2, x4, x5. And you can check with cross-validation. And now we've learned a new tool for this problem, which is let the computer do linear combinations of x1 to x5 in such a way to maximize the spread. And the first component there, because these are all very correlated, it'll be exactly like our 2-dimensional picture. The first component should capture almost all of the information. And so what I did in this problem, and again, we'll go over it on Tuesday, but just to give you what's going on. So if you do just single variable regression, I had this y1 versus x1, which turned out very good, and y2 versus x1 turned out very bad. And then I did forward variable selection. This is all stuff from the previous class, using different variables. Okay, and for y1, just 1 variable is the best. For y2, 4 variables is the best. Okay, but now you can do the whole thing with PCA. So PCA says, before you do anything, let's, instead of thinking about x1, x2 all the way up to x5, think about these special linear combinations of x1 to x5, so that PCA1 is the special biggest eigenvalue, PCA2 is the special second biggest eigenvector, and so on. And so we've transformed the data, and now you can run regression directly on the first component, right? So this is one way of reducing what you're looking at. You can try just on doing regression with the first component. And then you can also do subset selection. So you can say how many components do you need? And it turns out for y1, it's better to have 4 variables. And for y2, it's better to have 1 variable. So this is another way, another tool in your toolbox of reducing dimension is by first doing special linear combinations of the things and then doing regression. That's what they focus on in the video as well. Yeah?
Here when it's saying 1 predictor or 4 predictors, the predictors are the principal.
That's right, yeah.
Not the original.
That's right. So and you can read in the output, these are the models it tried. So first it tried doing a regression using just 1 variable, and it tried all 5. And of course we expect the first one to be the best, right? Because the first one is the most spread out. And that's exactly what happened, right? So trying the model with just PCA1 had a root mean squared error of 0.95, and the other models all had one of about 3. So this is an indication that PCA1 is a lot more important than the other ones. Whereas if you did that with just x1 to x5, there would be no reason that x1 is special, right? So once you do it in PCA land, things are actually in order. And that's the same thing happened over here, right? In PCA 1 and 2 together were the best by a little bit. Once 1 and 2 are in the model, then it starts to be out of order because it's all so close. They're all basically the same. If you have 1 and 2, you kind of know most of the stuff. And in fact, what did it find? 1, 2, 5, 4, and 3 was what it added. But yeah, so I found the best model was you just need one component, just the PCA one will tell you the best possible regression. You don't need to worry about the other components. Okay, so this is related to what they did in the video that you were supposed to watch. I know in the video they kind of like glossed over all the math details, so that's why I wanted to show you. And we're going to do more of this on Tuesday's class. There's some videos from, I think, technically chapter 10 of the book, but about PCA in the context of unsupervised learning. So we'll have more examples like this, and we'll go over it there. Okay, any questions or comments before we break? Okay, so we'll stop there. Let me know if you have any questions about your draft due on Sunday, but otherwise, see you guys next week.